Hi everyone, welcome to Stereochemistry part 3. Let's discuss the projection formulas. In this part, projection formulas of chiral molecules. We all know that configuration of your chiral molecule is three-dimensional. It is not very easy to depict on paper since it is having only two dimensions. Hence, to overcome this particular issue, the following four two-dimensional structures known as projection formulas will be discussed. First one would be the Fisher projection, second one is the Newman projection, and third one would be Sahar's, and fourth one would be flying wedge formula. Let us discuss one by one. Now, let us discuss the Fisher projection. Uh, Fisher projection, as you can see, it is represented in two different ways. The first one you can see the horizontal line, which is close to our view, which is represented in the solid line, whereas the vertical one is the dotted one. The solid ones are very close to our views, as you can see here in this case, the hydrogen and OH group, whereas the carboxylic group and CH2OH, which are represented in the dotted one, which stay away from our view. The characteristic feature of Fisher projection we can explain in two different ways. The rotation of your Fisher projection by angle of 180 degree about the axis which is perpendicular to the plane of the paper gives identical structure. However, similar rotation by an angle of 90 degree produces non-identical, that's enantiomers. Let's see how it works, where you can see simple example are glyceraldehyde, which are horizontal hydrogen and OH, whereas vertical lines aldehyde and CH2OH. When you rotate 180 degree this molecule, you get this particular structure, and when you give the priority, it leads to anti-clockwise because it starts from OH and then CH2 and CH2OH. It's a anti-clockwise. However, the least priority group which is placed on the horizontal line, hence whatever the outcome we need to take it in the reverse, that's R. Hence, when you rotate about 180 degree, whatever we get the outcome, the resultant one will be the identical one. While when we do the 90-degree rotation, for this particular example, same R glyceraldehyde, when you do 190-degree rotation, we get this particular configuration. When you give the assignment, the hydroxy gets first priority followed by CH4 aldehyde and then CH2OH. It is the AS because it's an anti-clockwise direction. Rotation is happening in the anti-clockwise direction. However, the one thing if you notice, the hydrogen is placed on the vertical line, that is away from our view, hence it is AS. Therefore, when you do 180-degree rotation of the same molecule, which is becoming identical, whereas when you do only 90-degree rotation, then you get the opposite configuration, that is nothing but inertia. Having seen the Fisher projection, next let's see the Newman projection. When it comes to Newman projection, in Newman projection, the carbon atom away from the viewer is called rear carbon and is represented by a circle that we can see in the next slide. The carbon atom facing the viewer is called front carbon and is represented as the center of the above circle, which is shown by dot. The remaining bonds on each carbon are shown by small straight lines at an angle of 120 degree as follows. Bonds joined to front carbon intersects at the central dot, whereas bonds joined to rear carbon are shown emanating from the circumference of the circle. Here we can see that clearly, the pictures clearly show that the front carbon, the three groups attached on the front carbon is clearly visible, whereas the back carbon, the groups are not visible, only that groups emanating from the circumference. And this is overall Newman projection where front carbon is quite visible, all the three groups, whereas back carbon has three groups, but we don't see clearly. And good example is N-butane, where this staggered conformation clearly depicting the with a good dihedral angle, whereas in the eclipsed one, a zero dihedral angle, the groups are facing each other. Hence, that will have the more steric as well as the torsional strain compared to the staggered one. Now, let's move on to the next one. Having discussed the Fisher projection and Newman projection, next one would be the Sahar's projection. When you talk about Sahar's projection, it is certainly different from the first two. The bond between two carbon atoms is shown by a longer diagonal line. The bonds linking other uh, substituents to these carbons are shown projecting above or below this line, what you can see here. Due to free rotation along the carbon bond, two extreme conformations are possible, the staggered as well as eclipsed one. The diagonal line, what you see here, the two groups are attached. Each end, you can see three groups are attached, two hydrogens, one methyl, and it could be in the form of staggered as well as eclipse. This particular projection gives clear view about the groups present in the molecule. Next, let's see how we can convert from one projection into another projection. A good example here is Fisher projection into Sahar's projection. The Fisher projection of a compound can be converted into Sahar's projection first in the eclipsed form by holding the model in horizontal plane in such a way that the groups on the vertical line points above and the last numbered chiral carbon faces the viewer. The one of the two carbons is rotated by an angle of 180 degree to get staggered form. That's nothing but more stable or relaxed form, where you can see that the fissure, the horizontal line, it's close to our view, whereas the vertical one is the away from our view. And whenever we convert into the Sahars, it should be the eclipsed one. Subsequently, we can convert into staggered because it's a more stable conformation, because Fisher projection, whenever you project, that would be in the eclipsed form. That eclipsed we have to depict in the Sahar's projection, where you can see the same one, and later on it can be converted into a staggered one. It's a more stable form since it has a good dihedral angle. Therefore, steric and torsional strain would be very less. Once you get the eclipse form, we need to just rotate 180 degree along C2 and C3 axis. Therefore, you get the staggered conformation.